All right, so let's begin. So welcome Nicolas Brisebarre from CNRS. So he will speak on rounding of transcendental functions.
Okay, thank you very much. First, I want to thank you a lot for the great invitation. Okay, it's a real pleasure to be here. So I'm from Lyon, from ÉNS Lyon. French system of research is very complicated. I work for the CNRS in the premises of École Normale Supérieure de Lyon. Okay, and today, so I'm going to present you a work that I'm doing currently with a colleague from ÉNS Lyon, Guillaume Hanrot. So we're both members of a team that is expert in computer arithmetic. Okay, and so I'm going to address a question that arose in the field of computer arithmetic. Okay, so first I want to present you the numbers I will work with all along the talk. Okay, just to make things clear. And please, you interrupt me each time you want to. Okay, don't hesitate. So the framework for the numbers we work with is a binary floating point arithmetic. So I'm recalling you what is a floating point number. So we are given an integer, a precision, p, a set of consecutive integers called exponents, bounded by E min and E sub max, and a finite floating point number x will be defined thanks to two integers. The first one, an integer whose absolute value is stuck between 2 to the p minus 1 and 2 to the p minus 1, okay, capital M, and an exponent, this is an integer, between E sub min and E sub max. Okay? So my floating point number, this is a dyadic number, okay, between 1 and 2, multiplied by a power of 2. Okay? And actually, there are several ways to represent a number on a machine, but floating point arithmetic is one of the most common as of today. And the importance of floating point arithmetic became so strong that in the 80s, the academics and industrial decided to establish together a standard for ruling floating point arithmetic. Okay, and now we can see the basic rules for floating point arithmetic written in the IEEE 754 standard. Okay, the first version was given in 1984, and there was a revision almost 10 years ago. Okay, and now that there's a second revision that is currently written. So there are many requirements about floating point numbers, and in particular, they distinguish certain formats for representing the numbers. Okay, so we will deal with these fundamental formats. The first one is binary 32. It's called single precision. It used to be called single precision. So here, the value of the precision p is 24, and the exponents are between these two values. Okay. Though this is a precision that you will encounter mainly in signal processing, for instance, video games also. The following one, binary 64, also called double precision, is the most commonly used precision for scientific computing. Okay? So it gives you 53 bits of precision, or 16 digits of precision, and the exponents are between these two values. The extended double is much less used. It's essentially used to give some, to make some intermediate computation when we target double precision. Okay, so here P is 64 and you have these values. And binary 128, quadruple precision, is also, as of today, seldomly used. One of its main use recently was in a work by the astronomer Jacques Lascar and his colleague that works on the stability of the solar system. And Lascar and his colleague launched huge computations in quadruple precision. But as of today, on the most current processors, you don't have the quadruple precision offered on the chip. So you have a kind of a emulation in software. Okay, so the floating point number I will work with in the talk will have this form, okay, with one of this value for P. Okay? Another immediate need is the need for rounding. Okay, we have a finite amount of numbers used to represent the reals, so we have to define quickly a rounding mode. Okay, so there are mainly 4 rounding modes defined in the standard. In the talk, I will focus on the most commonly used, which is round to nearest. Okay, so if x is a real number, the rounding of x will be the floating point that is the closest to x. In case x is the middle of 2 consecutive floating point number, you round to the floating point number whose integer significand is even. Okay?
Why is that? Why do you go to even?
Well, I don't think there is a theoretical justification. In practice, the occurrence of the rounding seems to be well balanced. Okay, so I don't think there's any theoretical justification for this. So what we call a breakpoint is a point where the rounding function changes. So when you use rounding to nearest, the breakpoint will be the middle of 2 consecutive floating point numbers. Okay, is it clear, this? So I will come back to this definition of correct rounding with drawing. Okay, so just an immediate definition. A correctly rounded operation whose entries are floating point numbers must return the result that you would obtain by computing exactly, I mean with infinite precision, the operation and then round it. Okay? So maybe you first envision the difficulty. I'm talking about an abstract mathematical value. In practice, the computer will use an approximation. So how can we guarantee that the rounding of the exact mathematical value will be exact to the rounding of the approximation that we use to compute? Okay, I will come back to this with drawing. So when you have correct rounding, it improves the quality of your computation significantly. First thing is you have an accuracy that is improved. For instance, you have a more refined interval arithmetic. You have also portability. What do I mean? If I launch the same computation on 2 different machines, I have the guarantee that the same correct result will be returned to me. Okay. Second thing, basically, at first, one could think that we don't have much structure when we work with floating point arithmetic. Imagine that even the sum of two floating point numbers has no reason to be a floating point number. Okay, so nevertheless, we try to give some other rules that give some structure, that equip floating point arithmetic with some structure. And in particular, if you have correct rounding, you know that your operation returns a unique, well-defined answer. Okay? So it's important because if you want to make some proofs, when I say proofs, I think of formal proofs using proof assistant like Koch or Isabelle or HOL. Have you ever heard of these tools? Okay, it's really useful to have correct rounding. Okay, it's a significant use for the proof assistant. So, what do we know currently for correct rounding? Since the first version of the standard, there was a requirement for correct rounding for the basic arithmetic operation and square root. It's easy to guarantee. The problem comes when you want to compute values of functions like the exponential, the cosine, cube root. Okay, so a whole family that we call elementary functions. There was, as you will see, this is what I'm going to tackle today. It's still a challenge as of today. There was significant progress since 85, but as of today, we still don't have a complete answer. Okay, so the last revision suggested correct rounding for elementary functions, but it couldn't require it because we don't know how to address this problem in the 4 basic precisions. Okay, I'm going to show it on my drawing. Okay, so
you have a dramatic example where lack of correct rounding caused problems. Is there such an example? I mean, well, when was that day? People had this example that caused that Intel chips, they discovered a serious error, and they're doing this primality testing or something like that. That cost Intel millions of dollars to recall.
I will come back to it very soon. We don't have such dramatic example, but we can discard the possibility that it occurs. You will see why. So I will work on 1, 2, okay, and I will work also with a function whose values lie in 1, 2, okay, and x is a floating point number. It has this form. So here I have one floating point number. Here this is the floating point number right after this one, and here this is the breakpoint. Okay, the middle of these 2 consecutive floating point numbers. So my mathematical value f of x is exactly here. Okay, if I round it, it's round to nearest. I return these floating point numbers. This floating point number. Okay.
But when you have all those complicated functions, you don't know where it is, right?
Exactly. This is the problem. So I use an approximation. For instance, a polynomial, a rational fraction, something like this, to compute value close as I wish to my exact mathematical value. Okay, so the computed value, this is fx tilde, and its distance to f of x is at most epsilon. An epsilon that I chose. Okay? So if epsilon has this value, we have this configuration. Imagine that my approximation is here. I round it, there's no problem. Now, assume that the value that I return, that I compute is here. The two rounding differ. Okay? Do you see the first problem here? So, a simple idea to improve the situation. What should we do?
Refine.
Yes.
But how about rounding one direction only?
Oh, but the problem will be the same, Alexei.
Oh, because
yes.
you're the other side.
Yeah.
If you have an integer point,
The problem is that if you have a breakpoint, meaning a point where the rounding mode change, if the abstract mathematical value and the approximation are not on the same side, you have a problem. Okay, whatever the rounding mode is. So here the idea you refine. Okay, so let's have the value. Okay, so in this case, we're finished. That's it. Okay, so
But how did you know that?
exactly. So what are the problems with the thing that we've just done? First question, yes. So how many times will I have to have the interval? A priori, I don't have a bound. Okay? In practice, I have, because the number of floating point numbers is finite. Okay, so I know that I won't have to go to iterate too many times, but still, it can lead to an important amount of subdivisions. So this is the first problem. Second problem, what is it?
What if your f of x is in the middle actually?
Second problem, exactly. You can refine, it will never end, okay? So, second problem, we have to be able to know in advance when f of x is a breakpoint, okay? Third problem, the epsilon that works should be uniform, okay? That means that it has to be known in advance, and it should guarantee a good rounding, a correct rounding, for any evaluation you perform. Okay, so there are three issues. What if f of x is a breakpoint? How about the number of refinement of subdivisions? Epsilon should be uniform. And moreover, epsilon should be as large as possible. Why? Because the smaller epsilon, the more complicated the approximation, the more expensive the computation of the approximation. Okay? You see? Good. So let's try to formalize it with some parameters. So here my epsilon would be a power of 2 to the minus n. I have two consecutive floating point number, the breakpoint here, So first thing, the breakpoint. We want to find an epsilon such that either there exists L such that, oh, there shouldn't be this inequality, f of x is exactly the breakpoint, or for all k in this interval, we know that the distance of f of x to the breakpoints is at least 2 to the minus 7. Okay? And as I told you, we want m to be as small as possible. Okay? Good. So this problem, this is what is called the table maker's dilemma.
And you want to find m for uniformly for every function?
Oh no, for a given function. Oh no. This would be. No, yes, no.
So you fix the function, but points can be anything. Like for the evaluation points don't. M doesn't depend on the evaluation point.
It depends on the format of floating point numbers that you use.
But not at the point that you will evaluate r.
No, that's why this is the meaning of uniform.
That's the meaning.
Okay, so on the whole set, so you choose a function, and you choose a precision p format, and then you should have an m that guarantee that you have either this or this. Okay. So. What could be the value for the optimal m? As I told you, we would like to have m as small as possible. So here I'm going to present you something that is highly non-rigorous. Okay, and you can even find some counterexamples where it is very wrong. Okay, so but it gives you, nevertheless, it gives a fairly good idea of the situation. So, if you look at the exact mathematical value, f of x, you look at its binary expansion, okay? So, you have the first p digits, and here also, okay? And then, it's from the p plus 1th digit that you decide where you round, okay? And as I told you, you have problems when you are very close to the middle of two consecutive floating point numbers, okay? And being very close to the middle of two consecutive floating point numbers, it's exactly saying that you have this shape. You have a 0, plenty of 1, or you have a 1 and plenty of 0. Okay, after the pth bit. Okay, is it clear for you? So we are going to assume, and this is a very strong hypothesis, that after the kth position, the probability of having a 1 or a 0 is the same. So the probability, in this case, of having k, in this situation, larger than k0 is 2 to the 1 minus k0. Okay? So that means here, you want to have k minus 1 consecutive 1 or k minus 1 consecutive 0. Now, if you consider all the floating point numbers in your initial interval, it roughly tells you that the number of values for which here k is larger than k0 is approximately 2 to the p minus k0. Okay? So, you see, you have p minus k0. So if k0 is larger than p plus 1, it means that there's no value for which you have k consecutive 1 or k consecutive 0. Okay? So this highly non-rigorous argument tells you that the optimal value for m should be 2p. Okay? So if I go back there, we expect that m should be 2p plus something small, but m should be something like 2p. But in practice, proving this bound is very difficult. So in double precision, Vincent Lefèvre from my team developed algorithms and implementations to address the case of the double precision, meaning p is equal to 53. And he was able to find the optimal m, okay, associated to floating point numbers that we call worst cases. So if you look at 2 to the x, so 2 to the x multiplied by 2 to the 52 gives rise to this value. Okay? So why is it interesting? So the 2 to the 52, this is the denominator. Okay, so don't pay attention to it. Here you have the rounding bit, and then you have a 0, and you have 60 consecutive 1. Okay? So it means that you are very close to a breakpoint, but if you perform your computation on 62 additional bits, you can decide the rounding. Okay? So actually, Lefèvre was able to prove that 2 to the x, for 2 to the x, in double precision, we have an optimal value for m, which is 113. Okay. So to answer your question, most of the time things, well, go very well, meaning that if you use precision p, the precision that you will need to perform correct rounding will be 2p plus something small. Okay. So so far in classical example, we were not able to find some catastrophic example, giving rise to a huge internal precision needed to ensure correct rounding. Okay, so just to remind, the kind of function we are working with are these elementary functions. Okay, nth root, the trigonometric function, the reciprocal, the exponential, the logarithm. So you remember that I want to solve these two questions. I will try to illustrate our approach on this first question. Okay, we want to find all the floating point numbers whose values is exactly a breakpoint. Okay, so we have to determine all the j, all the l in this interval, such that f of this floating point number has exactly this shape. So what's the state of the art regarding this? First thing, I want to recall you what I will call algebraic function. I would say that the function is algebraic if there exists a polynomial in two variables with integer coefficient, such that p of x, f of x is equal to 0, okay, for all x in the interval that we consider. Otherwise, I will say that my function is transcendental.
You only have the radical nth root, right? That's the only algebraic function in your list, right?
Yes,
Any other things?
The reason is the following. We mainly focus currently on the functions of the C mathematical library.
Right.
Okay. So yes, we mainly focus on nth root. So there was work done on algebraic functions by some colleagues. There are also some theoretical results about transcendental elementary function. So there's an old theorem that dates back to the end of the 19th century, called the Hermite-Lindemann theorem, that tells you that if alpha is algebraic, meaning that alpha is the root of a non-zero polynomial with integer coefficient, then exponential alpha cannot be algebraic. Exponential alpha is a transcendental number. So that means that, well, you see from the definition of the algebraic that a floating point numbers is any rational numbers, of course, is algebraic. So that tells you that the exponential of a floating point number, if you accept 0, cannot be a floating point number, cannot be a rational number. Okay. So in particular, we are sure that if f is the exponential, there won't be any value except 0, such that exponential of x will be a breakpoint. Okay. So there's a classical function that is a part of the that is in the C mathematical library. This is the Euler gamma function. And as of today, from a number theoretical point of view, we know very little about gamma. Okay, we only know that these values are transcendental. Okay, and regarding their irrationality, also very little is known. So, yes.
So if alpha is a floating point number, then exponential of alpha will not be a breakpoint.
You're right.
But
non-zero. If alpha is non-zero.
For some alpha that are not algebraic, E of alpha will be a floating point number.
Yes.
So you can. Even if you know that if you evaluate your function in floating point number, you could fall on a breakpoint.
No, because I am sure that if alpha is a floating point number, exponential alpha will not be.
Yeah, but maybe you want to compute E of f of alpha, and f is a strand function that.
If you compose function?
Yeah.
Oh, so
but you don't compose function.
No,
sorry.
No, it's a basic brick. No, your question is relevant, but I'm only talking about the evaluation.
At floating point.
Yes,
okay.
as basic brick. Yes.
Okay.
Yes.
Yeah, I mean, if you compose function, we know almost nothing.
Yeah.
Okay. So in the rest of the talk, I will assume that the function I will deal with are transcendental. Okay, and I will also assume that they are complex analytic in the neighborhood of the interval 1, 2.
Why do you focus on 1, 2?
Oh, just for the simplicity of the, just to make the talk simpler. Yes. Okay, and just a notation, just to fix the ideas. If G is a continuous function over AP, norm of G infinity AB is the maximum of the value of the absolute value of G of X over AP. So I want to find all the I and J that satisfies this equality. Okay? So that means that this function has an integer value. So what am I going to do? We are going to build together a trap. So we we construct.
I'm confused. I thought that all the functions are going to be irrational already. So why are you looking at rational function? I mean, rational value?
Oh, no.
F is not...
No, my function is transcendental.
Right.
But that does not mean that it can't have rational values.
But for that class of functions that you're interested in, we do know.
No, e to the 0 is equal to 1.
No, 0 is always excluded.
No, but for gamma, for instance,
gamma, okay.
For gamma.
Okay, so you have other functions.
If you want, if it's clear for you, keep in mind that f is gamma.
Okay. Then we don't know. Yeah.
Okay. So this is a transcendental function, analytic in the neighborhood. So of course we don't. I assume that the function was going from 1 to 1 2. Okay, so you have to scale gamma to have this, but keep in mind that f, for instance, is gamma, and we know almost nothing about gamma. Okay. Mm-hmm. So f is not the exponential. For the exponential,
yeah,
you don't have to tackle this problem. It has been solved 150 years ago. Okay. So what we are going to do is we cut our initial interval into smaller intervals, and for each interval we will compute two polynomials in two variables with coefficients, with integer coefficients, okay, such that this weighted evaluation over the whole interval give rise to a uniform norm strictly smaller than 1. Okay, why? I'm going to show you why. Assume that you have such an equality. So this is a number u, this is a number v. Now look at these two formulas. You plug u and v inside this inequality. It gives you that, you know that PLK of I to j plus 1 is in Z. Is it clear to you? These are integer numbers. The p's live there. So we are sure that it's an integer. Okay? But look, we also have this. And we know that necessarily it's an integer strictly between -1 and 1. Okay, it's 0. Okay, so we have two polynomials for which we have 0. So now we perform
two polynomials again.
So this is my job. I will show you how we construct two polynomials in two variables that satisfy this. Okay, if I assume that I already have computed these two polynomials. I will do this afterwards. But let's say that I have these two polynomials. I know that I to j plus 1 will be a common root to the two polynomials. Okay. Now I eliminate the variables, and that gives me the solution. Here, I have to, that's why our approach is heuristic. I have to assume that you have kind of algebraic independence between the two polynomials, okay, in order to have a resultant that is non-zero. Okay, so we are working with Guillaume to find some tricks to get rid of this assumption. But it's tricky. I have counterexample, and it's so tricky that this assumption is fairly common in cryptology. The initial idea of this kind goes back to Coppersmith 20 years ago that used it for cryptology. And Coppersmith, then Bonnet-Durfee and Stehlé in works related to crypto or computer arithmetic use also this heuristic assumption of algebraic independence. Okay, so this part will be heuristic. Okay, the
So
rest.
P and the two polynomials are algebraically independent if they have GCDs 1. Is that right? GCD with respect to which variable, x or y? There are two variables, right?
Well, actually, the condition that we have is the fact that they don't have a common factor, a non-trivial common factor. Okay, because otherwise, that will say that the pair I to j plus 1 lies on a common irreducible component. Okay, and except if I'm able to make some useful computation on this irreducible component, I will be stuck. Okay, whereas if I have non-zero resultant, I'm finished. I have all the possible values. Okay, so now, how do I construct this P1 and P2? So the first tool that I will use is Chebyshev nodes of the first kind. Okay, I will do interpolation. I will use interpolation at these nodes. So what we call Chebyshev node of the first kind, these are the zeros of the n+1 Chebyshev polynomial. Okay, so they are these guys. So why are they interesting? Well, the polynomial that interpolate a function at Chebyshev node are actually excellent approximation with respect to the uniform norm. So look, I will give several illustrations of this fact. So if you look at the error of approximation of a -1, 1 of f minus Pn, now you compare it to the best possible polynomial approximation. Okay, here you have norm of f minus q, and q is any polynomial of degree at most n. Okay?
Integer coefficient?
No, real coefficient. Okay, so this error is what is called the minimax error. This is the smallest possible error over all the polynomials of degree at most n. Okay, so and we see that the approximation error is fairly reasonable overestimation by a factor log n of the best possible error. Okay. Another illustration of this fact. If f is of class Cn plus 1, so it should be over -1, 1, sorry, at the Chebyshev nodes, then for any x you have this result, which is a kind of a Taylor-Lagrange formula. But if you remember, for Taylor approximation, you have this. You don't have the 2 to the n. Okay, so when you use Chebyshev interpolation, you improve the result by an exponential factor. Okay. So before stating another result, I have to introduce what is a domain that is the natural domain for studying Chebyshev interpolation or Chebyshev approximation. This is what we call Bannatyne ellipse. So a Bannatyne ellipse for -1, 1 has this form. Okay, so you're given real number larger than 1, and E sub rho has is defined this way. So let's have a look at various values of rho. Okay. So of course, if rho tends to 0, the Bannatyne ellipse tends to -1, 1. Okay. So for 1.05, you have this ellipse. 1.25, 1.45, 1.65, 1.85. Okay? So these domains are the natural domain to study the approximation by Chebyshev interpolation polynomials. Okay? And what result do we have? If you assume that your function f is analytic in a neighborhood of a given Bannatyne ellipse, E rho, then the approximation error is bounded by m rho of f, which is the supremum of modulus of f over the Bannatyne ellipse, divided by rho to the n multiplied by rho minus 1. Okay? So here you have a geometric convergence in rho. Is it clear?
What do you mean?
You fix f, okay? You fix rho. Now, what you can play with is the value of n, okay? And then in that case, m rho is a constant. You have here rho to the n plus 1. And as n tends to infinity, you have a geometric convergence, geometric rate of convergence. Okay? So this is fast. Another property that is a consequence of what I said before, but I think it's a fairly funny property. When you know the values of a polynomial at the Chebyshev nodes, you almost know the supremum norm of P. Okay? The supremum norm of P over -1, 1 is bounded by the maximum of the absolute values of P at the Chebyshev nodes multiplied by constant log n. Okay?
Is there any intuition why you get a log n?
The log n is related to. So you write your polynomial in Lagrange basis, and in that case, you can show that Lagrange basis, defined thanks to a Chebyshev polynomial, as how to show it?
Well, log of n is basically 1 plus 1 over 2 plus 1 over 3 up to 1 over n, right? So does that arise from that? Is that B or F that you wrote?
So P of x is the sum from 0 to n of P of mu k multiplied by L sub k of x.
Oh, that's the Lagrange.
Okay? Yes. Okay, so you have P of x that is smaller than the maximum of P and Q multiplied by the sum of the absolute value of x. Okay, and then bounding this sum.
That's about log n.
Yes. Okay. It's technical, but it's something that is feasible.
And it's k from 0 to n, right?
Yes, k from 0 to n.
So you get log n if it's like 1 plus 1 over 2 plus 1 over 3, 1
Yes.
over n. I mean,
Yes.
so is there a direct?
No, that's the you. Sorry, I can remember. There's no, I don't. I want to say something wrong.
Mm-hmm. So that's the log n. That's where you
Yeah.
get the log.
So the log n comes from the upper bounding of this sum.
Mm-hmm.
Okay. So that tells you that if you want to show that P is small, well, it will be sufficient to show that that P is small at the Chebyshev nodes. Okay? So keep in mind this information. So now we're back to a general function f. Okay? So assume that f is in Cn plus 1 of minus 1, 1. Pn is the interpolation function of f at the Chebyshev nodes. And we call Rn the approximation error. Okay? So we have the norm of f, this is triangle inequality, it's straightforward, is smaller than the norm of Pn plus the error. Okay, nothing smart. This one is smaller than constant log n times the maximum of Pn at the mu k, okay, plus the remainder, plus the approximation error. Okay, but Pn of mu k is exactly f of mu k. Okay, so here, which information does it give you? If you want to show that a function is small, it's sufficient to show that you have a small approximation error and f is small at the Chebyshev nodes. Okay?
Approximation error is in the sense of approximating by polynomial to the n.
Yes. Yes. Okay?
How do you bound that? I mean, Taylor's
Oh,
coefficient has
I
that.
bound this, for instance, with this. Okay?
I see.
Or with this value, which is less flexible because it imposes to be able to compute the derivative, okay, the n plus 1's derivative,
Right.
okay? For an analytic function, this is easier to deal with, this one, okay? So I have to be able to compute this, okay, and to make it small, okay, and I should be, and I also have, to make the values of f small on Chebyshev nodes. Okay?
But f is given to you. You have no control over it.
F is given to me.
Right.
Exactly.
So why do you say you have to make it small?
Oh, sorry, I should have, this is not, sorry, here I should have used another notation for f. This is not my initial f, okay? No. Here, this is a generic function, phi, okay, that I will use in my computations, okay? F is not an initial one, it's a stupid choice from me to have made it, okay? So just the only thing that I want you to keep in mind is that to have a function phi over a whole interval, it's enough to have a small approximation error and to have small values at the Chebyshev nodes. Okay? This is the only thing that you have to remind. So just something that is also straightforward, but necessary. I told you, I presented you everything on -1, 1. I will work on more general interval AB. There's no problem at all. You scale your Chebyshev node this way. Okay. And everything works perfectly well. Second thing that we'll use are Euclidean lattices. So I don't know if you have already met Euclidean lattices. Lattices are Euclidean lattice is a set of points that are regularly set in the ambient space. Okay? So, for instance, this is a part of a lattice. General definition: you live in R to the D, okay, and you consider K vectors that are linearly independent over R. Okay? And now you introduce the set of all integer combination over Z of the BIs. And this set is called a lattice, a Euclidean lattice. And B1, Bk is the basis of the lattice. Okay? So it looks pretty much like a vector space. Of course, there are many things that are not common to vector space and lattices, but still there are some properties that remain. And for instance, there is a notion of dimension. For a given lattice, all the bases have the same number of elements. Okay? So an example of lattice, Z to the D, or every subgroup of Z to the D. And this kind of structure is an incredibly powerful tool for modeling some phenomenon in number theory or computer science, for instance. Yes. So here I will use them to model my problem. And in particular, I will use a fundamental algorithmic problem that I'm going to show you now. So here, I have a basis for this lattice. And here, I have another basis. So question, which basis do you prefer? Which basis seems the more pleasant to work with for you? You see the structure, you see the two bases, okay? For you, which basis describes better the structure than the other? Erase the points. Okay? Now you're given only the basis. Which of the two bases gives you a better intuition of what is the structure? Alexei, which one?
Well, the one whose color matches
The black one?
Yes.
Yes. Because if you have the red one, to imagine just from the red one the shape of the lattice, I think it's not straightforward. Okay? Whereas with the first one, it's very natural. Okay? Which features seems to have this nice basis? The black one. When you work on a vector space, usually what kind of basis?
Yeah, orthogonal.
Yes, we like to work with orthogonal. Okay, so here, the black one, what is nice, and it's also a reason why we can imagine more easily the lattice from this basis. A nice feature is that the vectors are fairly orthogonal. Okay, so here this is a difference with vector space. We can't guarantee that a basis that we can have an orthogonal basis. Okay.
Actually, if I take the horizontal edge and a totally vertical edge too, that is orthogonal. Right?
She's suggesting to connect
Vertically above. Then you're in trouble.
If you skip one row and connect
Yeah.
0, 0 with
Go vertically up.
But which one?
No.
on the left.
From the origin,
Yes,
go vertically up.
but I have the right to go only to use linear combinations of these two.
Right.
Okay.
Right.
So-
Okay.
Okay. I can play only with integer multiples of u, integer multiples of v, and sum.
But this is 2v minus u.
So
So
if
you
you
can't go back. That
if you use-
go there, you cannot reverse. It's not invertible. No, but so you pose the problem you pose is somewhat underdetermined a little bit. You say what is the nicest orthogonal?
it is fuzzy. My question is
Okay.
vague.
All right.
Of course, my question is super vague. Yes. To answer your question, yes, you can have orthogonal vector, but here what I'm requiring
degenerate
is to have
entire-
a basis. Okay, the transformation that you were proposing cannot be reverted. Okay, so the notion of what is a good basis is something that can be made rigorous in dimension 1, 2, 3, and 4. Okay, because we have a notion, because here, look, we have vectors that are as orthogonal as possible. And in the Euclidean lattice, there is a notion that is an invariant, which is the volume. The volume is the volume generated by the basis of the lattice. What does that mean? Look at this parallelotop. You compute this volume. Okay, this is the volume of the lattice. Okay, and you know that whatever the basis that you consider, the volume will be always the same. Okay, and that implies that being orthogonal is analogous to having short vectors. Okay, so a good basis is a basis made of vectors as orthogonal as possible or vectors as short as possible. Okay, this definition is rigorous in dimension 1, 2, 3, 4.
Unfortunately, rigorous meaning it has a unique answer.
Exactly. Up to dimension 4, the first four shortest.
Actually, here you do have some ambiguity, right? I mean, 60 degrees or 120 degrees are both.
Yes, it's up to here,
up to sine.
Up to sine.
Yeah.
Up to sine,
So
you have uniqueness.
Yeah.
Yes, up to sine you have uniqueness.
Right.
Okay, so up to dimension 4, the first 4 shortest vectors form a basis. Unfortunately, from dimension 5, you can find basis. You can find lattices for which the 5 first shortest vectors are not a basis. Okay, so this problem of good basis has to be stated more clearly. But keep in mind that a good basis in a Euclidean lattice is composed of fairly short vectors, and which is similar, fairly orthogonal vectors. Okay, so an algorithmic problem that is fundamental in the algorithmic of a Euclidean lattice is the shortest vector problem. You're given a lattice, and the requirement is to output a shortest non-zero vector. Okay, so in dimension 2, there's the classical Gauss algorithm for quadratic forms that outputs a shortest non-zero vector. But as the dimension goes to infinity, this problem is NP difficult. Okay? So it was a very important result when, in 1982, Arjen Hendrik Lenstra and Laszlo Lovász proposed an algorithm that gives an approximation solution, meaning a fairly short vector, in polynomial time. And since then, this algorithm has had many important applications. So, what does LLL output? You're given a lattice of rank k, of dimension k. LLL will return you a basis that is composed of pretty short vectors. In particular, its vector B1 is an exponential approximation of the norm of a shortest non-zero vector. Okay? So it doesn't output you a shortest non-zero vector, but you have, at worst, an exponential approximation, exponential in the dimension of the lattice. Okay? And it does it in a polynomial number of operations. Okay? So, you remember I mentioned an invariant called the volume of a lattice. This is the volume generated by the basis. And LLL returns, in particular, two vectors that can be, whose norm can be estimated thanks to the initial volume of the lattice. We will use these two inequalities. Okay? So, keep in mind that if I have a small volume of my lattice, LLL will be able to return two small vectors. Okay? Okay, so it was just to define the volume. So back to my initial problem. So I'm looking for two polynomials in two variables with integer coefficient whose uniform norm over a given interval AB is strictly smaller than 1. I want to construct two polynomials that satisfies this inequality. So to do it, I will discretize the problem. I will plug Chebyshev nodes. Okay? And instead of looking at the continuous requirement, I will tackle a finite number of such requirement. Okay? I replace the uniform requirement by a condition on the Chebyshev nodes. Okay? This is what I'm going to do. You see what I mean?
I'm confused. Yeah.
So here I want to build two polynomials, okay, such that we have this inequality satisfied over a whole interval. Why? I don't know if you remember. It's because that if I have a floating point number x such that f of x is a breakpoint, then I am sure that it will be an integer. It will be an integer stuck between strictly -1 and 1. Hence, it will be 0. Okay, so this is my goal. But here, I have a uniform condition over a whole interval. The idea is to use, instead of a continuous number of inequality, I will focus on this inequality specialized at the Chebyshev nodes. Okay. I want to find two polynomials such that pk, evaluated here at Chebyshev nodes, is strictly between -1 and 1. Okay? And the idea is that if P1 and P2 are small at these Chebyshev nodes, we saw it together before, P1 and P2 will be most certainly small on the whole region.
I guess you could have stated this without giving us two polynomials, right? Because this is a problem for a single polynomial.
Exactly.
Right, okay. So,
Yes.
so I mean, eventually you want two, but right now you can state it.
Exactly.
Okay, so a bit confusing too.
Yes,
Two
yes.
polynomials.
You remember when I use f instead of using a function phi, when I said, I show you that a function, to be small, should be small at the
Right.
Chebyshev coefficient, at the Chebyshev nodes. Okay,
Right.
this is the same thing that I use.
Right.
Okay.
But you don't need two polynomials for this then.
No,
Right.
no,
Okay.
no.
All right.
But I need to guarantee this for two polynomials.
Oh, why?
Because I want then to have these two conditions satisfied, okay, in order to have the elimination, to have the possibility of eliminate one of the two variables.
That's the next step, I guess.
If I have this, I know that I will have okay. So I and j are this one, and I want to find P1 and P2 such that I to j plus 1 is a root, common root to P1 and P2. Okay.
Wait, I'm lost. How do you use these two polynomials in this? What are you using?
Once I have obtained
Right.
these two equality,
Right.
this is when I have to make my heuristic assumption on the algebraic independence
Okay.
between P1 and 2.
All right.
I perform some elimination, and then I get the values of I and j. Okay? It's just to derive I and j eventually.
By what do you do to get the I and J?
So I can compute a resultant. I can use answer lifting also.
There are two unknowns, so we need two constraints to obtain a system of two equations and two unknowns to be able to solve the system.
Yeah, but this, you're solving this in on integer points, right? I mean, on
Yes,
points.
you're right. You're right. And I have two unknowns. That's why I need to build two polynomials. Because if I consider only one polynomial,
How do you know you can always build two polynomials?
I don't have the I know that I will, thanks to LLL. I know that I can construct two polynomials, that's for sure. The problem for which I have no guarantee is the fact that their resultant won't be 0.
All right, sure.
Okay? So, I want these inequalities to be satisfied at the Chebyshev nodes. Okay, so I discretize the problem. I want this and this to be small for all k. So I'm just rewriting this condition. That means that this vector should be small, and this vector should be small as well. Now I rewrite this vector as this sum. Okay, so these are integer coefficient, and these are vectors. Okay, but these two elements belong to this lattice. Okay, so that means that the vectors composed whose coordinates are the value of P1 and P2 at the Chebyshev nodes. Okay, they are all elements of this lattice. And I want these two vectors to be small. That means I want to compute short vectors in this lattice. Okay?
What's the dimension of the lattice?
So, I haven't talked about it. Yes, I need to introduce it now. So, the dimension is function of the monomials I am considering in the writing of my polynomial. Okay? So, an optimized basis, choice of basis, is this one. Okay? So, we use weighted basis, and so just to realize what it means. Corresponds to 1 x xd f of x x f of x xd minus 1 f of x f d minus 1 x x f d minus 1 x. Okay, so kind of triangular basis. This is what I use, and I can explain. There is a strong reason why we choose this basis.
So this is a single vector.
All the here, it will correspond to xk, y, j, and okay, to deal, just to see the monomials I have to consider. Okay. So this is a triangle set of monomials, and the number of such elements, this is d plus 1, d plus 2 divided by 2. Okay, just a triangle. So the dimension of the lattice, this is this one. So my initial problem now is this one. I want two polynomials with this shape satisfying this inequality. I discretize, I plug Chebyshev nodes. I know that if P1 and P2 are small at these points, they are small on the whole domain. Okay. So, as I told you, we define a lattice. We have to solve shortest vector problem, an SVP. Now, we want, you ask me, are we sure that we can find P1 and P2 small enough? If you remember, when I defined LLL, I gave you two inequalities for the first two vectors. I told you B1 and B2 are small if the volume of the lattice is small. Okay? So now my work is to prove that the volume of the lattice can be made as small as desired. Because if it's the case, I am sure that my vectors will be small. Okay? So my P1 and P2 will be as small as I need. Okay? So, just to remind you, I'm using this basis. These are Chebyshev nodes. And the volume, so this I can show you why if you ask. The volume of my lattice is bounded by this expression. So you have power of 2 to the p. You have an expression that comes from x evaluated on the Bannatyne ellipse. Okay. Here you have a supremum of f that comes from the remainder. Okay. And at the denominator, you have rho to the n minus 1 over 2. Okay. So n, this is d square. This is the presence of this rho to the d square that will make it possible to have the volume as small as possible. Okay. So what does this give you? If you plug rho equal 2 over b minus a, you get volume smaller than 1. And in that case, you see that if you use d is equal to a big O of p, so a degree d equal to big O of p, you are sure that you have the whole the answer for gamma on the whole interval AB. Okay? So if AB is the whole interval, 1, 2, we get an answer in less than 1 hour for the double precision. And in currently, it's a sage math algorithm, and so it has to be implemented in C and improved. But it is 1 CPU year for the quad precision. Okay? Don't be terrified by this amount of time. With a better implementation and the use of several cores, it's something that is not at all horrible.
So you have done this?
No, not yet. We don't have launched intensive computation. We know that we have this 1 CPU here because we launch partial computations over, let's say, 2 weeks. And then, as it is more or less always the same kind of computation, it's honest to return this estimate. And there are functions for which we can improve this result. Okay, so we can search for, given the function, optimized value of rho, and in that case, for the exponential, the choice of big O of p over log p for d makes it possible to tackle the whole interval 1, 2.
Well, for exponential, why do you have to solve this problem? You know it's transcendental.
Oh, you're right. So I can, yes. So do you want me to explain why I'm saying this?
Yeah,
Okay.
clear. If it doesn't take too long.
Yeah.
So it's a different problem you're trying to solve.
Actually, when you use this approach, you have a byproduct. So you remember that the second problem that I will keep for today is to show a uniform distance.
Oh, I see.
To the breakpoints.
Then you need exponential.
Okay, and I need the exponential.
Oh, I see.
Actually, the approach I've just showed you gives more than what I showed. Okay, I focused on the quest for points, integer points over a curve. This is what I did, actually. Okay, but what we can prove is that when using our method, I will not give the details because I will lose you. Using our approach, we can guarantee that if we don't have integer points of the curve, actually, we have more than this. We are able to provide a kind of exclusion zone, exclusion area for the presence of integer points. Okay? Mm-hmm. So the method I've just shown you gives a non-trivial result for the table maker's dilemma.
Technically, you can get such bounds from current results in transcendental number theory, but the bounds are terrible.
The bounds are terrible.
What is M if you get, say, what's the best bound you use?
Oh no, I forgot because it was my first attempt 15 years ago, and
right.
this is
I'm
terrible.
Sure it's terrible.
This is terrible.
Yeah.
Yes.
And whose result would you use for the best? Not Baker's theory, or some better bounds.
Well, so there. I can show you. So recently, more recently, so when I started thinking of this problem 15 years ago, the bounds were terrible. Mm-hmm. In 2011, two researchers showed that. So you remember that I told you that we expect that the intermediate necessary precision should be 2p, approximately.
You expect?
We expect
I
this.
remember you said that, but I don't remember why.
We expect.
Why do you expect 2p?
Oh, there are several reasons, but the first, the reason that I gave you was based on a highly non-rigorous argument, saying that if you look at the binary expansion of a number, so consider the first p bits, okay, and then you look at the other bits, being close to a breakpoint means that you have either a 0 and plenty of 1, consecutive 1, or you have a 1 and plenty of consecutive zeros. Okay? Mm-hmm. So the question is, how long can be a chain of 1 or zeros?
Right.
Okay?
Right.
If you assume that the probability of getting a 1 or a 0 is 1/2.
Oh, I see.
Okay? Then the probability of having p consecutive 1 or p consecutive zeros is 0.
Right.
Okay? And this is non-rigorous.
Right.
Because you can find counterexample.
Right.
Okay? That's why you expect to have m equals 2p.
Okay.
Okay? So you expect to have 2p, and if you use transcendental number theory, the best results that you can get are, so for p equal to 53, so you expect to have, let's say, 106, 110, and we have this value, okay? So it's 300p instead of 2p. And for quadruple precision, we get 400p instead of 2p, okay? This is much better than what was proven before, but still, you can't use them in practice.
Mm-hmm. Right.
Okay? So just to, well, how can I conclude? Yes, just for the result that we get. So the best thing we hope to prove is to address this kind of inequality. Okay? So for the double precision, it was solved 15 years ago by Vincent Lefèvre. He did it algorithmically. and his algorithm is a kind of extension of Euclid algorithm, and the complexity is in big O of 2 to the p minus 3. Okay. And Damien Stehlé gave an algorithm in big O of 2 to the p over 2, and that made it possible to solve the table maker's dilemma for the extended double precision. Okay, but unfortunately, these algorithms are not practical at all for the case of quadruple precision. Okay, and unfortunately, as well, our approach with Guillaume does not give significantly better results for the solving of this inequality. On the other hand, so a nice feature of our work is that we're able to solve a relaxed version of the table maker's dilemma. Okay, so if we want to solve this inequality, so m here is not anymore 2p, m is 6p, 8p, or 10p. Okay, the approach that we're developing with Guillaume makes it possible to answer the question. Okay, the other two algorithms, Lefèvre and Stehlé, are not practical, but whereas ours is. Okay. So currently, what we are able to do is to have results for the exponential, for instance, for m equal to 6p. Here again, it's the time is in CBU years. Okay, it will need to launch very intensive computations. But so far, it was impossible to tackle this case. So this is with our approach, it's the first time that one is able to envision a satisfying answer using a certain amount of intensive computation. Okay? Okay. And our goal is that, if you remember, I told you that there was a standard launched by the IEEE in 1984 that requested correct rounding for the basic arithmetic operation. And in 2008, they suggested correct rounding for elementary function, but they didn't require it because no one was able to answer. So we hope that once we will have launched our computation, will give some support for the requirement of correct rounding for the 4 main precisions and for all the elementary functions. Okay? So I will stop here. I thank you very much.
Any additional questions?
Do you think someday we will go to occ precision? What's the next one after quad? Are we going crazy already? I mean, already I think IEEE, precisions, strictly so accurate that the error in the last bit is like the distance between here and California, and the error is the thickness of a paper. That's how accurate, if you the error in one single double precision is that accurate. Well, if you're trying to fly to Mars, maybe maybe that's not good enough. I don't know.
You might miss it.
Huh?
You might miss it.
You might miss it. Many things have happened. Well, actually, I think there are lots of other things that come into play way before that happens. But it's a bit hard to conceive of how already 64 bits is that accurate. It's very hard to conceive.
Yes. As I told you in the introduction, there are very, very few applications
Right.
as of today that use quadruple precision.
Right. Yes. So, yeah. So I don't know.
It's not common, and I think it's available on PowerPC chips, but it's not available on the other chips.
Yeah.
So
no,
because
very few people need it.
people don't ask for it.
Exactly.
So
Yeah.
So I don't know if it's true, but I heard that people are developing less precise arithmetic because all the computations they do in machine learning, etc., they don't need precision.
Machine
So
learning is
actually,
so
they are
fast,
interested in chips that do a lot of computation, but with
Yeah.
less precision. So maybe
no, you're perfectly right. No, but the answer is it depends on the application you target. Of course, there are plenty of people that don't need at all correct rounding. Yes, that for a video game, for signal processing, you don't care about correct rounding. Okay, it's mainly a basic brick for people that do rigorous computation, certified computations. Okay? So if you need to make mathematical proofs by a computer, for instance, or any kind of rigorous computation, then this is a useful basic brick. Otherwise, no, there are plenty of people that don't care about quality computing, of course.
Other questions? Okay, thank you.
Thank you.
Thank you.